Yes, today we are going to look at Physics IGCSE question 0625. That's 0625, alternative to practical, variant 1 for year 2019. Now let's check the first question here. A student is determining the weight of a meter rule using a balancing method. Figure 1.1 shows the apparatus. Now you can see the apparatus here. The student places the meter rule on a pivot. He places a load P on the meter rule at the 90 cm mark. Now this is the 90 cm mark. You can see it here. There is a load there at the 90 cm mark. Let me use red so that you see it clearly. 90 cm mark. Keeping the load at the 90 cm mark, he adjusts the position of the meter rule on the pivot so that the meter rule is near as possible to being balanced. He records the distance A from the 90 cm mark to the pivot. This is the distance here from 90 cm mark, and this is the pivot here to the pivot. He records the distance B from the pivot to the 50 cm mark, and that is the distance you have here to the 50 cm mark. Now let's continue. He records the distance B from the pivot. Okay, I've said that. He repeats the step, placing the load P at the 85 cm mark, the 80 cm mark, 75 cm, and 70 cm marks. Let's look at the readings below. These are the readings for A, and then these are the readings for B. Let's check the question now. This is the question. Plot a graph of A in cm on the y-axis against B in cm on the x-axis. You do not need to begin your axis at the origin 0, 0. Now when you hear something like that, that you do not need to begin your axis at the origin, it means when you are choosing your scale, you don't need to start your scale from 0. So we are going to look at the table and see how we are going to plot our graph. But first, the first thing you need to do when plotting a graph is to just show your axis. Here is A in cm, and let's look at the second one, B in cm too. We have B here in cm. With what I've done here, you've gained 1 mark in IGCSE. Now let's look at the table. The first point we have in A is 21, and then B 19.1. But we need to choose our scale first. So let's look at the maximum value of A and the minimum value of A. The minimum value of A is this, 10.5, and the maximum value of A is 21.0. So you need to choose a scale in such a way that it will contain most of the points on the graph, and then it will satisfy these two conditions. Remember, we were told that we may not need to start from 0. So let's check how we are going to do that. Okay. Let me just put something like this. Okay. Cross here. Cross here. So I am going to start this one with 10. Then the next one, 12. Let me write this properly. 12. The next one, 14. The next one, okay, 16. The next one, 20. Oh, sorry, we have 18 before 20. So let's have 18. And the next one, 20. So you have chosen a very good scale for the x-axis. You've chosen a very good scale for the x-axis. For the y-axis, I mean to say. So let's now go to the x-axis. Now for the x-axis, the minimum value of B is 9.5 and the maximum value is 19.1. So let's look at the scale, 9.5, 19.1. So I am going to start this one with 9. If this is 9, let's make this one 11, because your graph must cover a greater part of the graph sheet. So this is 13, 9, 11, 13, 15, 17, we make this one 19. Let me clear this one and write it somewhere. We make this one 19, 19, and this is 21. So this is our axis B in CM. Okay, the next thing to do is to plot our points on the graph. The first point being 21.1, let me plot from there, 21.0 and then 19.1. So let's look at it. This needs to get to 21 if I'm not mistaken. So let's have this one as, or can we still increase this? Can we still increase this? Yeah, I think we can still increase it. It's too small. It's too small. So let's have it here. We're going to have this one as 12. So this is 14. The next one is 16. The next one is 18, 20, and 22. Okay, let's plot our points now. Let's plot our points. The first one, 21.0 and 19.1. This is 21.0 here. Then we need to look at the point that is 19.1. 19.1. Let me reduce this one a little bit. Let me reduce it a little bit. A little bit. I will still make it a little wide. Just trying to reduce it. I will still make it a little wide. This is 19. So let's look at 19.1. 19.1. This is 19.2, so 19.1 should be a little bit. Okay. 20, then we have here as 19.1. 19.1 and 21. What I do normally is to use cross. So this is my 21, and where is my 19.1? This is my 19.1. So this way, 19.1 and 21. Okay, the next one is 18 and 17.2. 18 and 17.2. 18 here and 17.2. That one is straightforward. 18 and 17.2. This point, 18 and 17.2. The next one, 16 and 14.1. 16, 14 is here, 2, 4, 6, 8. 14 is here, and we have 14.1. So it is this point, 16 and 14.1. Now 13 and 11.8. This is 13, and this is 11.2, 11.4, 11.6, and 11.8. Exactly this point. Okay, then we have, oh sorry, 13 should be here. 16, let me check again. Okay, this is 21 and this is 19.1. This is 18 and this is 17.2. Then the next one is 16 and 14.1. 16 here, and this is 14, 2, 4, 6, 8, 14.1. So it's here. 16, 14.1. The next one is 13 and then 11.8. 13 is here, 2, 4, 6, 8, 10. 13 and 11.8. 13 and 11.8. And the next one is 10.5, 9.5. 10.5 should be around here. This is 10, 1, 2, 3, it should be here. 10.5 and then 9.5. 9.5 should be here. 1, 2, 3. So 10.5, 9.5. That's all. So we have our points. The next thing is for us to plot our graph. What you need to do is to draw a line of best fit. And how do you draw a line of best fit? To draw a line of best fit, the first thing you need to try is to look at the first and the last points and check if you can pick the first and the last point and all other points fall within, around, and they are scattered in the same direction, then you are right. So let's look at this one. I'm going to pick the first and the last point and see whether we are in order. Let me put it on the first one and then try the last one. Oh, that's cool. This is cool. There are 2 points that are not on the line, and the 2 points are scattered in different directions and they are very close to the line. So this is a perfect one. Yeah, we've done our graph. Let's check the next question. Determine the gradient of the graph. Show clearly on the graph how you obtained the necessary information to determine the gradient of the graph. What you need to do is to pick 2 points on the graph. Remember this usual formula for gradient: y2 minus y1 divided by x2 minus x1. Okay. With this, what I will do is to draw a triangle. Let me use another color. A triangle. I'm going to pick from here. Let me pick from here. I'll draw, and then let me end it here. Okay. Here, yeah. Okay. And then I pick it from here, pick from here, and end here. So I think you can see that line. For drawing this triangle, IGCSE will also award you marks. So if you look at this point, there is a point here. There is a point here. I mean this point here. If you trace the point down here, what will it give you? Let me make it bigger. If you trace this point down here, if you trace this point down here to this side, it falls here. So it's going to give me 20.4, 20.4, and this one will give me 12. So what I have is 20.4 minus 12, 20.4 minus 12 divided by, let me see the second one. We have 17 here. Okay, let's check. 1, 2, 3, 4, 5, 18. 1, 2, 3. 18.6. So we have 18.6 18.6 minus what? Minus 11. So what will this give us? This is going to give us 20.4 minus 12, that's 8.4. 8.4 divided by 18.6 minus 11 is 7.6. If I am not making a mistake, 8.4 minus 7.6, let me see. Can I use a calculator here? 8.4 minus, okay. 8.4 minus 7.6, let me see, calculator. Oh, let me make it smaller. Okay, 8.4 minus 7.6, 8.4, why is it not coming? Delete. 8.4 divided by, what am I dividing it by? I think 7.6, 7.6, and that is what, 1.105, 1.105, 1.105, 1.105. So our answer here is 1.10. Let me write it properly. 1.105. Let me just leave it in two significant figures. So I'll have it as 1.1. That is my gradient. I'm having my gradient as 1.1. So let me write it 1.1. Now determine the gradient. Show clearly let me see, this is point 1.1. Okay, let's see. You have to show clearly on the graph how you obtain the necessary information, and that is what I have shown here. I have shown this, how I obtain the information by drawing the triangle, and then this is our gradient. The next one, calculate the weight W1 of the meter rule using the equation W1 equals G times P, where P is 1, So I don't need much calculation here. If P is 1 and our G is 1.1, so this one is also 1.1. Suggest one practical reason why it is difficult to obtain accurate readings for A and B in this type of experiment. So why is it difficult to obtain accurate reading? This is a moment experiment. The first thing I want you to look at is that it may not be easy for you to obtain balance. So you have difficulty in obtaining balance. Difficulty in obtaining balance. That is a reason. Well, you can also state reasons like the pivot is not sharp enough, difficulty in judging the center, or you can also say the load may slip. Let's see, let me add that too. They are only expected to just state one. Load slips, or pivots not sharp. So these are reasons that you can give. Let's go to the next one. Now the student measures the mass of the rule on a balance. Write down the mass M shown on the balance in figure 1.2 to the nearest gram. The mass here is 102.65. So to the near 112.65 to the nearest gram, it is going to be 113 grams. Let me change this thing to red. 113 grams. 113. I think red is clearer. 113. Calculate the weight W2. Weight W2 of the meter rule using the equation W2 equals mg. W2 equals mg. So how do we calculate that? W2 equals mg. M is 113 grams. But if you look at the unit of G, it is in Newton per kilogram. So that means we need to convert this 113 to kilograms. So we now have 113 divided by 1000. And that gives us what? 0. That's point, let me make it clearer. 0.113. And what are you supposed to do? You have to multiply it by 10. And that will give you 1.13. 1.13. The next question is for you to state and explain whether this value W2 can be considered equal to value of W1 obtained in part C. What did we what was W1? 1.1 and W2 is 1.13. What is the difference? In fact, the two can just be rounded down to the same. So I will say yes. I will say yes. State and explain whether it can be considered equal. The first thing to do is to state whether it can be considered equal. So yes. And why? Because, because they are within the limits of experimental accuracy. They are within the limits of experimental accuracy. Let's go to the next question. Now let's look at this question. A student is determining the resistance of a resistant wire. The circuit is shown in this figure. Now, the first question is for you to record the current I in the circuit. Now, don't make this mistake when recording the current. You need to look at this thing and know that it is between two lines here. Now, so we have 0.2, this should be 0.3, this is 0.4, and this should be 0.5 here. So this should be 0.42, 0.44, 0.46, and in between 0.46 and 0.48 we have 0.47. So the answer should be 0.47, and then the unit of current is ampere. We need to put the unit there. Let's go to the next question. Now the next question, let me make it a little bigger. The student places the sliding contact C at a distance L equals 20 cm from B. She records the potential difference V across the length of the resistant wire. She repeats the procedure using L values of 40 cm, 60.0 cm, 80.0 cm, 100.0 cm. All the readings are shown on the table. Calculate and record in table 2.1 V over L for each of the values. Complete the V over L column. V over L. The first one, V is 0.5, so you have 0.5 divided by 20. 0.5 divided by 20 will give you 0.025. I'm just going to write the answers as you just do the same for all. This one is 0.92 divided by 40.0. So I'm just going to write the answers 0.025 for this one. The next one is let's see, 0.023, 0.023. The next one is sorry about this, 0.027, 0.027, 0.027. This one, 0.027, and the next one is 0.026, 0.026, and the last one is 0.024, 0.024. Okay, so we have our values now. Look carefully at the values of V over L in now. Okay, we have completed the table, but we've not written the units because you have to complete the VL column heading. The unit is V, that is volts, divided by L, that's centimeter. So the unit is going to be volts per cm. So it's volts per cm. That is the unit you need to put here, volts per cm. That's the unit. Now, look at this table. Tick the box to show your conclusions from the result. Let's look at it. V over L is approximately constant. Let's see. 0.025, 0.023, 0.027, 0.026, 0.024. Actually, if you look at all these values, they are just between 0.024 and 0.026. So they are approximately constant. But let's check the other reason. V over L is decreasing as V increases. No, from this. There is no simple pattern. No, we've got to tick box 1. So, now let's look at the next one. Justify your conclusion by reference to your results. Justify your conclusion by reference to your results. Now, looking at the results are so close. So, the first one, if we look at V over L, for the first one, it is 0.025. If you come to the middle, 0.027. You come here, 0.026, 0.024. So the values are very close. Values are very close. So that's my justification. Values are very close from the table. You can also use our common word within the limits of experimental accuracy. Okay, let's go to the next one. Next question here. Calculate the resistance of 100 cm of the resistance wire using the formula. This is the formula you have to use. R equals V over I, where V is the potential difference across 100 cm of the resistance wire. Use the value of current from part A. Give your answer to a suitable number of significant figures for this experiment and include your units. So we are to use the current we got from this place. Oh, where is the current again? Okay, not here. Let's check the next one. Okay, 0.47 was the current that we got. So our current here is 0. Okay, wait. Our current is 0.47. So how do we get our V? How do we get our V? Okay, let's look at it critically. How do we get our V? Now we are talking about 100 cm length of the wire. Calculate the resistance of 100 cm of the resistance wire. Now let's look at 100 cm 100 cm. What was the voltage we got for 100 cm? We got 2.4. So we are going to use 2.4. Our voltage is 2.4. 2.4. Now divided by 0.47. Remember, we got the 0.47. We got the 2.4 from here, and we got the 0.47 from here. So what is the answer? 2.4 divided by 0.47, which will give you 5.11. So we are going to write our answer as 5.11, and you put the unit of resistance, which is ohms. Now let's go to the next question. In this type of experiment, it is sensible to keep one temperature of the resistance wire, the temperature of the resistance wire, as close to the room temperature as possible. Suggest one way to minimize the rise in temperature of the resistance wire. How do you minimize rise in temperature of a resistance wire? We know that when current increases in a system or in a wire, the wire emits heat. So for us to keep the temperature constant, we need to keep the current low. We need to keep the current low. You have to suggest one way, but I'm going to give you two. One, keep current low. Two, now when you keep the current constant for a long period of time, there is this possibility that heat will be emitted. So why not switch off between readings? So you can say switch off between readings. So any one of the two is actually correct. The next one is for us to draw the circuit symbol of a variable resistor. Well, circuit symbol of a variable resistor, well, as simple as you think this is. I want to tell you some things that you must not do. Now, I want to draw this line like this. This line must not enter into this box. And then the second one, this is the second line. Let me use another, let me draw a line, draw a line so that it's going to be cool. And then I have this here. I also have this here. So this is the symbol of a variable resistor. Let's go to the next question. Now the next question. A student is investigating the rate of cooling of water under different conditions. A greater rate of cooling occurs if there is a greater change in temperature during the same period of time. Figure 3.1 shows some of the apparatus. We have the apparatus here. The thermometer in figure 3.2 shows room temperature theta R at the beginning of the experiment. Record the value. We are to record this value, theta R. So let's check, let's look at it. Theta R, we have 20 here, 21, 22, 23, 24. So we have 24 degrees centigrade or Celsius, as the case may be. So make sure you write your degree this way. Don't write it at the bottom. Okay. The student pours 200 cm cube of hot water into the beaker. She records the temperature theta of the hot water at the time t equals 0. She immediately starts a stop clock. She continues recording the time and the temperature reading every 30 seconds. The readings are shown in table 3.1. So let's check the table for our readings. Okay, we have the readings here. The student repeats the procedure using a metal can painted matte black in place of the beaker. The readings are shown on the table. Complete the column headings in table 3.1 and in table 3.2. How do we complete the column heading? You have to write the unit of time in seconds. It should be small s anyway. Okay, I think, okay, yeah. So, and this should be in degrees Celsius. We have the same here, S, and we have in degrees Celsius. Done. Okay, the readings are shown complete. Look carefully at the readings in table 3.1 and in table 3.2. Tick the box to show your conclusion from the readings. Let's look at the boxes we have here. The water in the beaker has a greater rate of cooling than the water in the can. Let's check. Let's check the rate of cooling. This is the temperature. It is reducing. I don't think so. The water in the beaker has a smaller rate of cooling than the water in the can. From our results, no. There is no significant difference between the rates of cooling of the water in the beaker and the can. That is what we are going to go with. There is no significant difference. I'm going to show you. Okay, there is a question on justify your conclusion by reference to the readings. Okay, let's look at the readings. We have 94 here, and we have 89 here. 94, let's compare. 89. 93, 87. Can you see that they are close? 94, 89, 93, and 87. They are so close. Let's look at another one. Okay, can we just check the difference? 94 minus 89 is 6. 93 minus 87 is 5. So this is my conclusion. I can say comparing the rates, the difference between the highest temperature, let me see what I will quote there, the difference between the highest and lowest temperature of the beaker is 6, and that of the can is 5. Let me write that again. Okay, let's have it. Okay, the difference between the highest and lowest temperatures for the, which one is coming first? For the can, okay, for the beaker. For the beaker and the can are 6 and 5 respectively. So you can now quote it this way: 6 and 5 respectively. Let me put it here. Can I bring these together? Okay, so that means we have 94. You need to quote this: 94 minus 89 equals 6 degrees Celsius. You have that one. Then you also have 93 minus 87 equals 5 degrees Celsius. Okay. The next one. Now, a student in another school carries out the experiment and reports that the rate of cooling of water in the can is different from the rate of cooling of water in the beaker. He plans a change to the experiment to find out whether this difference in the rates of cooling is caused by the matte black surface of the can being a better radiator of thermal energy than the shiny surface of the beaker, the metal of the can being a better conductor of thermal energy than the material of the beaker. Suggest 2 suitable changes to the apparatus. You see, from here, a student repeated the experiment using a metal can, painted matte black in place of a beaker. So let's look at this. Suggest 2 suitable changes to the apparatus that the student could make, because the students report that the rate of cooling of the water in the can is different from the rate of cooling of water in the beaker. So because of that, he plans a change to the experiment to find out whether that is caused by the matte black of the can being a better conductor than the shiny surface of the beaker, or the metal of the can being a better conductor of thermal energy than the material of the beaker. So what do you need to do? Yeah? The can was painted black. So I think what we could change is to also paint the beaker. We need to paint the beaker to know whether it is the matte black that is causing it. So the first one, what you need to do is to use black painted beaker. Use black painted beaker with the painted can. That's the first one. Black painted beaker with the painted can. Okay. With the painted can. Then you have to switch now. You now use a shiny can with the painted beaker. I believe you understand what I'm trying to do here. We are changing the conditions. Use a shiny can and a painted beaker. A shiny can and a painted. All right. Suggest 2 variables that should be controlled in order to make the experiment a fair test. The variables to be controlled to make the experiment a fair test. Of course, to make it fair, you need to use the same volume of water. So let's have volume of water. To make it fair too, we need to use the same starting temperature. Same starting temperature. I'm going to give you one model. I'm only going to write 2 here. Same starting temperature and room temperature. Now, state 1 precaution that you would take in order to record accurate temperature reading. You see, when you are having an experiment that has to do with, heating water, heating a liquid, different volumes of water, you want to compare temperature, you must ensure that the thermometer does not touch the beaker. That is one. Then secondly, you must continue to stir the liquid. So, I'll write now. Stirring the liquid. Ensuring the thermometer does not touch the beaker, and then viewing thermometer readings perpendicularly. What I mean by this is when you are viewing, your eye must be perpendicular to the direction of the thermometer. All right. I think this is we are getting to the end of this paper. This is the last but one question, so let's go to the last question.
Okay, let's take the fourth question. A student is investigating the work required to pull a box containing some masses up a sloping wooden board. Figure 4.1 shows the board and the box. Plan an experiment to investigate how the work required to pull the box up the slope depends on the mass of the box and its content. Work done is calculated using the equation work done equals force times distance moved in the direction of the force. The following apparatus is available to the students: a wooden board, a box with a length of string attached, a selection of masses that fits in the box, a meter rule, and an electronic balance. In your plan, you should list any other apparatus that you would use. You should take note of this. Explain briefly how you will carry out the investigation, including the measurements you will take. State the key variables that you would control. Then draw a suitable table. Note these two. Draw a suitable table with column headings to show how you would display your readings. You are not required to enter any readings in the table. Then also explain how you would use your result to reach a conclusion. You may add to the diagram if it helps you. Okay, quickly, let's go to what we are required to do. List any other apparatus that you would use. Okay, you have to compare work and mass, but in your calculation you need force and you need distance. So to measure the force, you actually need what we call a force meter or a Newton meter. That's what you actually need. You need a force meter or a Newton meter. So I'm going to write it, the apparatus you need. Okay, apparatus, force meter, Newton meter, or you can use pulley with weight arrangements. Pulley with weights, my spelling, weights, okay, arrangements. Is this still correct? Arrangements. Okay. This, okay, you need this. So let's go to the second question. Explain how you would carry out the investigation, including the measurement you would take. If you look at this, there is a string here. So you start by adding a mass into the box, then attach the force meter or Newton meter to the string and pull up the slope at a certain distance. Let me quickly put that here. Add a mass to the box, attach the force meter to the string and pull up the slope at a certain distance. Pull up the slope at a certain distance. After doing that, you now record the distance moved, and the force. Oh, measure, let's say measure and record. Measure and record, because that's what you need to calculate your work. Measure and record the distance moved and the force. Okay. Now the next thing to do, since you've been given different masses, you say repeat the process above for 3 other masses, each time measuring the force and the distance. Each time measuring the force and the distance. Okay, let's check the next question there. State the key variables that you would control. What are the variables that need to be kept constant? 1, this slope, the angle of this slope must be constant, and or you say the height of this wooden block must be constant. Then the distance must be constant. So let's look at it. Variables. You say height of block, or you say angle of slope must be constant. Height of block or angle of slope must be constant. That is the first variable. As a first variable. Also, distance must be kept constant. So let's take the next question. Draw a suitable table with column headings to show how you will display your readings. You are not required to enter any readings on the table. From what we have there, we are not required to enter any reading on the table. We just need to draw the table. So here you go. Let's draw our table. Okay, let me bring this one up. Let's draw our table. You have our table here. You have our table here. The distance is constant anyway. So from the table you have masses. Yeah, let's have, okay, let me put my mass in kg. The unit of mass is kg. And then I also have my force. These are variables. My force in Newton. Remember, our distance is a constant. Our distance is constant. So we've drawn the table. Let's look at the next thing. Explain how you would use your result to reach a conclusion. Now, to reach a conclusion, you can say plot a graph of work done against mass, because you are comparing the mass. Or you can also say calculate work done in each case and compare with mass. Or Calculate work done in each case and compare with mass. If you can do it like this, then you get all the marks for these parts of the question. Let me see, is there any other question there? No, that means we've answered all the questions. That will be the end of our solution to IGCSE past question today. If you love what I'm doing on this channel, I would like you to subscribe to this channel and then, hit the notification bell icon so that you get notified anytime I post a new tutorial. Thank you. Please like this video and share. Bye for now.